So, we'll like now we will look into fire resistance, we have looked into severity, effect of fire on structures we will look into, but first let us see how does the temperature in a room varies and get some idea. If I want to find out theoretically or why, I said ventilation factor AW into HW to the power half, why it is so, that is we will look into. So, what people have seen is, in case of a fire or fully grown fire beyond the flashover, beyond flashover point, with time you find that in the beginning, if I look at the height of the building, this is the floor, this is the ceiling. So, this is a compartment, again experimental work. So, in the beginning, initially you will find the temperature at the top is and bottom is average. We are talking of average gas temperature or air temperature. Gas, because it will have product of combustion also, the gases, gas temperature within the room, average if I take, it is somewhat higher at the top, and as the time passes this goes further something like this, and when it is fully grown, in fact you have very little, it is almost more or less a constant temperature you can think of. So, temperature of the compartment or the room remains by and large constant with height, except for a small portion close to the floor where it is somewhat varying. So, I can assume a constant gas temperature, as we call it, constant gas temperature within the room, constant gas temperature within the room. So, you can talk in terms of constant gas temperature within the room, and you can see typically this can go up to 1000 etc., depending upon the fire load and so on. So, we assume gas temperature is constant within the room, all right. Post flashover temperature in a room can be assumed to be uniform. It has become same, because everything has caught fire now, everything is burning. So, temperature would be more or less constant. Now, this is in a simple compartment as I talked about. This is what the scenario would be. This is the room, this is the room, this is the room compartment, let us say, and this is the this is a opening, and hot gases will go out from the top. Hot gases go out from the top. Hot gases goes out from the top. Hot gases goes out from the top, and fresh air enters from the bottom. And there is somewhere there is something called neutral plane. Somewhere something called neutral plane, where actually it is a boundary between hot gases going out and cold fresh air entering. So, the pressure difference should be 0 there. Here the pressure should be higher, pressure on this side should be lower, and here the pressure should be higher, here pressure should be lower there, Now, you can understand this, of course, you can understand this. Why? Because the density of the pressure is given by rho GH. So, it depends upon density. Now, if the hot gases will have lower density, right, hot gases will have lower density and air will have higher density. So, we can actually look into the scenario. For example, let me consider this diagram again at the bottom. P1 is here, 1 is here, 2 is here, 3 is a point here, and 4 is a point there. 3 and 4, or let me use black color, that would be better. This is 3, this is 4, this is 2, this is 1. Pressure at 1 must be more. Pressure must, pressure, basically the direction of the flow is like this. So, pressure should be somewhat from this, outside, just outside point 2 should be, because here there are hot gases. So, pressure should be, there should be a flow along this direction. So, pressure should be higher somewhere here, and in this case pressure should be somewhat higher. So, this will be the actually pressure diagram, or even relative pressure or velocity. If this pressure is 0 here, so pressure diagram is somewhat there. So, let me call this height as H0 and this is called as HF. Now, H0 or H oxygen you might call it, where fresh air is coming in, and here the flume, the fire basically. So, HF. So, HF and H0. So, P3 is the pressure here, P4 is the pressure here, pressure must be here more, and pressure here actually is more negative. So, let us see how I can express this pressure. Let us see how do I express. So, for points 1, 2, 3, 4, point 1 and 4 are inside the compartment. 1 is inside the compartment, 4 is inside the compartment, 2 and 3 are just outside, 3 is outside and 2 is just outside. So, you can actually find out the pressure difference between these two. Now, this pressure is a function of y, because if this is my y, this I define as y, any point from this point I call it as y, this is y, at any point here is y. So, this is my, let us say this is my datum, origin I call it 0, and this pressure. So, I can get an expression for pressure at 1 and 2 first, and then 3 and 4 first. Now, pressure at 1 will be lower than the pressure here, right. So, it will be P0, if it is outside pressure is P0 minus rho g h, rho g h minus rho g h, or h is actually y. So, at any point y it will be written like this, rho 1 the density here minus g into y. So, y, any distance y I am considering from here, rho 1, and P0 is outside pressure, and P0 rho g, rho 0, rho 0 is outside density, 1 is the density here, and rho 0 g y. So, that is what it is. Now, this value is smaller than this value, because this is at higher temperature, and there is a negative sign here, there is a negative sign here. So, the pressure difference would be P1 minus P2, because P0 minus rho 1 g, rho 1 is rho 1 is inside, and rho 1 is actually less. So, I am subtracting less quantity, here I am subtracting more quantity. So, therefore, this is what is happening. So, P1 and P2 I can express like this. Similarly, P3 and P4 I can express like this. So, rho 1 and rho 0 are densities of gas inside and outside, they are respectively. Gas on going out would expand, as soon as it gets out it will expand, because the space is now full, and it will attain the same density as the outside density, right, and attain nearly same density as outside. So, that is the concept that we are trying to deal with. Then let us look at 3 and 4. Let us look at 3 and 4. Now, at 3 and 4 again it would be P0 rho 0 g y and P0 rho 4 g y. Now, rho 4 would be again less, because we said that nearly constant temperature prevails into the room. So, temperature of gases inside will be higher. So, their densities are lower. So, rho 4 is less than rho 0. So, therefore, the I mean basic but the y height here, the y the height there h is positive, and this is what will actually see this is somewhat higher, rho 0 plus, actually this should be rho 0 plus, because rho 0 is here plus the excess pressure would be rho 0 g y, because there is a minus sign this. See, my datum is here. So, this is negative y is negative, right. So, this effectively becomes plus, this effectively becomes plus. Therefore, if this is plus, difference would be this, because this is larger value, this is smaller value, this rho 4 is less than rho 3, y is negative here from this datum, P0 is the outside air pressure, which is datum. So, y is now pressure here will be less than the pressure here, and this y is actually that I can take by taking y as minus sign. So, that is how the flow occurs in this position. So, this is how we can express both this, y will be minus. So, for negative values of y, P3 and P3 are greater than P0. Actually, they are both greater, one is still more, another is slightly less more. So, flow takes place in this manner, right. This is understandable now. So, that is why you can see that this this diagram P0 is here, P3 is more, P4 is there, P1 is here, P2 is there, you know. So, correspondingly, because this was y is positive here, y is negative there, and that is why, you know, this is how it is. So, y positive neutral plane, y positive, that is what it is. So, that is how the pressure difference would be, right. And then we can use Barnolies equation. Now, anybody is an architect here? No. So, normally this Barnolies, I also derived Barnolies equation quickly in a quick manner to recollect it, so that you know, and those people who are in architecture, they may not have studied a fluid mechanics. So, I have normally been deriving this. So, if somebody is an architect, they can look into Barnolies equation otherwise, but it is fairly simple to derive this kind of an equation, because if you consider the flow through an element like this, stream flow, there is a streamline, right, and it is inclined in this manner. This length is delta S, this length is delta S, direction of flow is like this, pressure here and area delta A. So, P into delta A is the force acting here, and P plus rate of change of pressure with S multiplied by ds. So, that is the pressure acting here, multiplied by the dA. So, that will be the force here, right. In addition to this, the mass of this is acting, density is rho g delta A, delta S, that is the volume element, delta S is the length, delta A is the area. So, all the forces we can equate, right. We can actually equate. This angle is theta, let us say. So, this angle is theta. So, if we equate these angles, just for your recollection, one can write velocity also as a function of, one can write velocity. So, this forces we can equate, we will do that, but just let us do one thing more. Let us write velocity. Velocity will be varying with distance. So, rate of change of velocity with s multiplied by ds, plus it might vary with time, dt. V is a function of t and s. Let us assume that v is a function of t and s, but if we assume steady, then t part will go. Let us generalize it a little bit. So, acceleration is dv dt, it will be written like dv ds, ds dt and dv dt, because acceleration will be simply dv dt. So, this could be written as, because when I am trying to equate the forces, I need the acceleration also. Since the fluid is flowing, mass into acceleration must be equals to all the resultant forces acting along the direction of the flow. So, acceleration is given by dv ds v plus dv dt. That is how, it is a simple derivation, there is no complication involved in it, right. So, that is same one I am writing again. Applying force balance, P minus delta A minus this part minus rho g delta A, that is the mass, into ds sin theta. Now, this force along this direction I am interested in, and this is, you know, this should be this component of this one along this direction I am interested in, whichever way. So, it will have one component there, one component there. Now, this is, if this is theta, this will be, and this is, you know, this is rho g, ds sin theta will be this distance, ds sin theta will be this distance. So, I am multiplying rho g dA ds sin theta, that is the force that is acting, that must be equals to the mass rho delta A delta S into acceleration. That is all causing the flow. I am simply writing the force balance. The one force is the pressure difference, pressure here and minus the pressure here, and then the component of the force acting here, component of the force acting here. So, this must be the total force that is acting, and you know, must be equals to mass into acceleration, mass into acceleration. So, if I do a little bit of further, now sin theta can be simply written as dz. You know, if this is the height difference, dz by ds, sin theta will be written by dz by ds. So, I write sin theta here again and replace sin theta by dz by ds. So, sin theta is, this one rest all will cancel out, as we can see from here, this will cancel out, p delta A terms, this will cancel out, leaving del p del s minus, you know, I can just put that rho g. So, this is what will be remaining, minus with a minus sign, and this is rho g del A del S sin theta. I will be replacing by del Z by del S, and then is right side this cancels out from everywhere. P delta rho delta A will cancel out from everywhere, rho delta A, and also delta S will cancel out from everywhere next. So, I will be left with minus del rho del S, g del S has cancelled out, dz by rho g, rho should also go out, no, rho remains, rho g remains actually, rho remains here, because this did not have rho, this term did not have rho. So, rho g remains actually. So, rho g remains, delta S cancels out, finally it comes out to be this. And if I assume steady flow, what I get is minus del B del T etc., just divide everything by rho. So, this will get divided by del B del T is equals to V del B by ds, V del B by ds divided everything, and this will be divided, this rho will cancel out, only this part divided. So, this is something like this. So, in a steady situation, this term can be put equals to 0, dB dt is acceleration terms can be written like this, and for steady flow this is equals to 0. Then I can integrate this whole thing. So, in steady flow this is equals to 0. So, therefore, integrating V del V, right, V del V plus 1 by rho del P plus dg del Z, integrate all of them, because del S, since right hand side is equals to 0, del S will not be there anywhere, and you get B square by 2 plus P by rho plus Z equals to a constant, because I am integrating it, right hand side is 0, if I integrate I get a constant. That is simple derivation of Barnolies equation, you would have studied in much more details. Since you are most of you are engineers, that is not a problem. So, Barnolies theorem is velocity head, pressure head and datum head, sum total must be constant in a steady streamline flow, steady stream flow, right. So, in our fire case also we can assume that the steam flow is occurring at the top as well as the bottom, and we can apply Barnolies equation, and it is steady, because we are assuming the fully developed fire constant is going, we are not measuring time variant scenario, we are not taking account here, right. So, that is what it is. So, total pressure, or you can say total pressure is constant, total pressure is constant, you can write it like this in this manner. So, rho V square by 2 pressure, pressure is rho V square by 2 in pressure unit, it will be like this, and head unit it will be something like this, right. So, for gas flow from 1 to, now I can apply this to point 1 and 2. So, at point 1 pressure was P1 and divided by rho 1, pressure 1 divided by rho 1, and if the velocity is there, that will be V square by 2, and since they are at the same height, so Z I need not take, 1 and 2 are at the same height, it was in the same height in the compartment, if you recollect, it was in the same height in the compartment. If you recollect, what we said was it is something like this, this is the window, this is the window. So, 1 was somewhere there, 2 was somewhere there, therefore, 1 and 2 are the same height. So, that can be, that is ignored, and this is the velocity at that location at distance y by 2 and P1 by rho 1, P2 by rho 2, etc., etc. Similarly, for 3, 4 also I can apply, but let us do for 1 and 2 first. So, V1 will be 0. Why V1 will be 0? Because it is a bulk, it is inside the room, actual velocity is just close to the window only, and V1, one can assume V1 is equals to 0, because it is bulk in the room from where it is coming. So, I am comparing inside the room, if you recollect, it was in this corner. Similarly, 3 is here, 4 is just inside the room. So, 2 is just outside the window, So, that is what I am interested in, that velocity actually. So, V1 can be considered to be 0, assumed to be 0, no net directional flow. The pressure difference is due to confinement of hot gases, because hot gases are confined there, therefore, that is why there is a pressure. The volume is fixed here, and outside it goes into expand and the pressure is reduces down. And once it is out at 0.2 at atmosphere, it would expand and the density would change to nearly atmospheric condition. So, hot gases flows, so gas density is used in the denominator. So, velocity is 0 and outside density will be rho 0, inside density will be gas density, right. So, that is what it is. So, this was the pressure in 1, if you recollect, rho 1, that was the gas, and G y divided by rho 1, and here rho 0 G 1, well this will take it as rho 0 gas temperature. I mean this should be 2, rho, this should be 2, rho 2, this should be 2 V 2 square by T 2. Now, this I can write further, get an expression for, now yeah, at this get an expression for yeah, since the volume, I am not considering the volume, sorry, there is a problem, little bit of problem. Since the volume of the gas I am considering this, this density rho 2 also I am taking as same gas, because hot air is going out, so hot gases flows. So, gas density in both the cases we are using as rho 1 only, where pressure we are using rho 0 and rho 1 there. So, if you now find out the V 2, get an expression for V 2, you will get an expression for V 2 from this one. Simply V 2 I can separate out and I will have P 0 cancelled out from both the sides, and this side if it goes it will be rho 0 minus rho 1, G y would be there divided by rho 1. So, V 2 square to the power half twice will come here, rho 0 minus rho 1 G 1 by rho 1, that is how it will come. The velocity there would come like this, velocity will. So, it is at any point y above the datum, the velocity will be given by this formula. And if I am interested in flow, then what I should do? I should take a small element dy, because it will vary, velocity will, pressure varies in this manner, velocity will also vary correspondingly, pressure varying in this manner, in this parabolic manner, and this side it was varying in this manner, pressure is changing, velocity will vary accordingly. So, at any distance y I find out the velocity given by this formula, above I find out. Supposing I consider a small dy element, then the flow will be simply area of the window, I mean the width of the window multiplied by dy into the velocity as a function of y, integrate this from 0 to h w by 2, height of the, because we are assuming approximately this will be, so one can do that way, but we will see how we are doing, slightly physically I am trying to explain you. So, I can find out the flow, quantity of flow of hot gases outside, and also find out the quantity of fresh air inside, the volume. Okay. So, that is what it is. So, supposing we use a nomenclature or subscript F for compartment gas and 0 for, or O for ambient one, 0 for ambient one. So, this will be rho 0, rho f, because rho 1 is rho f and this is also rho f, hot gases, and velocity of hot gas is given by this G y to the power half at any distance y from the neutral plane, at y distance above the neutral plane. So, this is what we tried to arrive at, and this is what we get, So, velocity of flue gases, that is why f at a distance y from the neutral plane is given by this formula, Now, for 3 and 4 I will do the same thing, and if I do the same thing, V 3 will be 0, the no net flow, because it is away from the room, V 3 will be 0, no net flow, it will be away from the room, and the pressure difference is due to the hot air inside, which has got a lower density, and it acquires temperature on entry at the room, and the density would change. So, again density would change inside once it enters, it will get compressed, the fresh air will get compressed, and then of course the combustion process will continue and change to the hot gas which will move. So, outside air flows, so air density is taken in the denominator in both the cases here. So, you see this is like previous one, this is what is done. So, at a distance y from the neutral plane, this will be the formula. At V3 we are assuming it to be 0, because there is no net flow, directional flow away from the room, and in the same manner I derive a formula B4 P4 rho 4 minus rho 0 by rho 0. Now, rho 4 would be what? Rho 4 would be rho f. Rho 4 would be taken as rho f and 0 remains same. So, this is how we get my expression. So, V air oxygen flow V0, which denotes the oxygen flow, VO whatever you call it, it denotes the oxygen velocity of oxygen or air at a distance y below the neutral plane is given by this. Now, I can calculate out the flow. So, mass flow rate I can calculate out for flow gases, it would be Vfy into dy integral. As I said, small, you assume now, consider a small dy element above the neutral plane. Velocity here is Vfy. So, the flow is area into velocity. So, what is the area? B is the width of the window. Let us say B is the width of the window. So, B dy is the area into velocity and 0 to Hf, where Hf is the height of the window above the neutral plane, right. Usually we assume to be half, but even if it is not half, does not matter, it can be depending upon the, if there is a outside air velocity, there is a wind flowing, then the whole thing gets distorted, wind can change the whole thing. So, it need not be, also depending upon the, we will see that later on sometime, some cases neutral plane need not be half, but everything is tranquil, no air velocity outside, then it will be something like this. So, that is what it is. So, B into, so this is the flow, this is the density of the gas multiplied by a coefficient CD, because you can, we are assuming streamline flow in almost all in, even when you calculate out wind load, you will find there is a coefficient which is utilized, because lot of assumptions are used. CD is what is called discharge coefficient, it is called a discharge coefficient, because physically we understand these are the factors which will actually affect the density. This is the volume flow multiplied by density gives the mass flow multiplied by discharge coefficient. So, this should be the flow, but there is a discharge coefficient which takes care of all unknown factors and all that. So, B window width is CD is discharge coefficient, all right. So, mass flow of oxygen is similarly one can obtain, mass flow of oxygen one can similarly obtain as V0 y dy and minus H0 to 0 now, because y is H, right. So, negative, right. So, and rho 0 is a, so this two we can find out, right, and actually this Hf plus H0 must be equals to H, because Hf is the height above the height of the window above the neutral plane, H0 is the height of the window. So, I can change this, I can integrate this anyway, because this expression for Bf is known to me in terms of y, and expression for B in terms of y is also known to me. So, continuing with the same mass flow of gases, that is what we have seen. Now, if I can express this further a little bit, because put the value of Bf as a function of y, which was coming like this, and there is hardly any complex integration here. This velocity was y to the power half. So, only thing that will come out is y to the power half dy, and rest all are constant. So, B comes out, C D discharge coefficient, density of the gases, B comes out, and this part also comes outside to the power half, and this is what it is. Now, if I integrate this, I get what? Y 3 by 2 to the by 3 by 2. You know, y to the power half, you integrate y to the power half, you get y 3 by 2 divided by 3 by 2, which would become 2 by 3, and h f to the power, if I put the limits of integration, I will get h f to the power 3 by 2, h f to the power 3 by 2. Now, B into h f is what? B into h f, B into h f, well, is the total area of the window above the neutral plane. Similarly, B into h 0 is the total area under the neutral. So, that means then h f and multiplied by h to the power half still remains. So, we can see that right now. You can see that mass flow of oxygen, similarly same integration, now it is minus y to the power half and dy minus dy. So, I just put it in the perspective, negative perspective, etc., etc., because x equals to y, dx is equals to dy. So, limits will change accordingly. So, you know, because this was dy. So, because it is negative. So, accordingly every limits will change, and I will get again h 0 minus h, because 0 to minus h f, there is a minus sign involved, and it finally comes out to be in the same manner as C d rho 0 b h to the h 0 to the power 3 by 2. This is simple, you can look into it, there is no complexity really involved. And mass flow, thus, you know, we use mass flow, this is mass flow rate actually, this is flow rate, velocity multiplied by area. So, per unit time. So, this is the mass flow rate. So, we might write m dot, that is mass flow rate. Mass flow rate we can use, subscript remains the same. So, we can use m dot f, mass flow rate, we can denote it by m dot f 2 by third, etc., etc. And similarly, mass of oxygen flow, mass of air flow, we write it in this manner, Now, actually sum total, you know, I can do a summation in some manner. 1 kg of fuel, supposing 1 kg of fuel, 1 kg of fuel reacts with r kg of air fully, because there has to be a stoichiometric ratio. Whatever air comes in, all of it will get assumed. For the first time, let us assume that everything reacts and produces 1 plus r kg of the combustion product. So, the ratio between these two must be related to this, you know, 1 by r plus r, because whatever hot gases is generating, whatever is coming in, same amount is going out. So, what, you know, so there is this mass flow rate of air and the hot gases, the flue gases, it must bear a ratio with the stoichiometric quantity. So, I can say that since 1 kg of fuel reacts with r kg of air, for wood one knows this, but if it is non-stoichiometric, that everything is not burning, everything is not everything is not burning, whatever combustible product is formed, everything is not reacting, then I will take a fraction. So, let us say it is phi. So, only r is a combustible, so phi is a, if there is a partial combustion, not everything is combustion, right. So, 1 kg of fuel reacts, not all the product of pyrolysis is burning, only a portion of it is burning. So, R should have actually complete burning would have consumed R amount of oxygen. Since it is partially burning, so R by phi amount of it is its oxygen is getting consumed, and the product that is coming out is 1 by R plus 1 plus R by phi. So, this ratio should be, this ratio I can find out, and if I do not assume, if I assume phi equals to 1, if I assume phi equals to 1, this ratio must be related to 1 by R by R. This ratio must be related to 1 by R. So, if I take this ratio, let us take this ratio, this cancels out, this cancels out, this cancels out, this would be there, and from here actually this will also cancel out from inside, the other things would be there. So, rho f by this term will also cancel out, because this is same both the places. I will be left with rho f, it should be other around, m 0 h f is fine by h 0, this should be rho 0 by rho f, rho f, because rho 0 would go up there, right, rho 0 and to the power half. So, this is all will be remaining, this is all will be remaining. So, ratio of these two must be equals to, ratio of these two must be equals to, this ratio must be maintained, this ratio must be, yeah, I think this is fine, this is corrected here, that is right. Rho f, why is rho f? Oh, acha, this rho f cancels out with this rho f, all right, that's fine, that's fine, that's fine, that's fine, that's fine. I think I did a mistake in algebra. This is rho f here, rho 0 here, rho 0 to the power half, so it remains rho 0 to the power half here, rho f to the power half here. This is correct, actually, this is correct. So, this is how it is, this is how it is, and this must be maintained. Now, ratio, this ratio must be same as the stoichiometric ratio, this ratio must be same as the stoichiometric ratio, and that is how it is. Obtaining after substituting mass flow rate, this is obtained after substituting mass flow rate. Therefore, I can get an expression for Hf by H0 in terms of rest of the things, Hf by H0, because this can be separated out, and the half is there, the so this is to the power, if I square both sides up, this goes away, this goes away, I will be left with rho 0 by Hf, rho 0 by rho f, this will come here, and Hf by H0 to the power 3, and then put 1 by 3. So, Hf by H0 I can find out, right, Hf by H0 I can find out. I have another equation, H0 plus Hf is equals to 1, H0 plus Hf is equals to capital H, height of the window. So, I can replace everything in that terms, I can replace everything in that terms, right, I can replace. So, Hf can be written as H0 like this, and H is equals to H0. So, I can write it in this manner. The other equation, the ratio of H0 is and can be obtained, this we can obtain now, H by H0. If it is half, then Hf by H0. So, if one can get this expression using typical value of point r is equals to 0.57. Now, stoichiometric requirement of air or oxygen or amount of air for 1 kg of wood requires 5.7 kg of air for wood, and densities of this 1.ρ0 and rho f vary from 1.8 to 0.5, rho 0 by rho f vary from, that means fewer the plume or the fire, the gases have got a density, ratio of density of air is, the air density is around 1.2 kg per meter cube. Air density is 1.2 kg per meter cube. Value of this typical smoke and gases is known to us, and this ratio varies from 1.8 to 5, there is a large variation as you can see. And so, the ratio for phi is equals to 1, generally this value turns out to be this rho 0 by rho f, this whole thing, this ratio turns out to be 0.3 to 0.5 for phi equals to 1. So, if I take this value is equals to 1 by putting relevant values, for example, this value somewhere average. So, 6.8 divided by 2 is 3.2. So, I put this equals to 3.2, this equals to 1, this as 5.7, then I can get a value of H0 by Hf, which will work out to be about 0.3 to 0.5, 0.3 to 0.5, right. So, 0.34 to 0.2, generally the ratio is 0.3 to 0.5. So, what is it? The bottom area is about 30% to 50% of the window height. Bottom area is about 30% to 50% of the window height. In other words, you can write everything in terms of H. You can write H0 in terms of H. So, I'll just so we can write H0. So, mass flow rate, this is H to the power 0. Supposing I write it in terms of H, capital H, right, because I know H0 by H is about 0.3, 0.4, etc., taking some value, some fraction. So, I can write in terms of H, and if I write to the power H, some fraction will come out. So, CD B into H to the power 3 by 2, B into H to the power 3 by 2 will come, this part. Rest all of course values are approximate values. We take rho f by rho 0, as I said, we take rho 0 is 1.2 kg per meter cube, and this Correspondingly, I can take an average value dividing by 3.2. So, G is known, all these are known. So, this part if you see this is the related to the wall area, this is related to the one area, this is related to one area, right. So, B h to the power, so area of the window into h to the power half, that is what it comes. I think we will stop here, next class we will look into, next class we will look into, okay. So, that is what it is.